let's see if we can get one more video in before the sun goes down. In this video, we're going to talk about rectifiers and voltage clamping circuits. So recall the half-wave rectifier that we saw in the last video, where we know that the circuit looks like this, and on the positive half of the AC signal for our source voltage, we know that we're going to charge up this capacitor C, but then it's going to try to discharge through this resistor R. Now what's the downside of having the half-wave rectifier? Well, all of this negative cycle, per se, for the source is wasted. Nothing useful really happens with it at all. So what we do is seek to be more efficient, as we always try to, and what if we could make a full wave rectifier such that we can use that negative cycle for something useful? The question is, can we do that? Yeah, it's not too crazy. The circuit looks a little bit odd here, so we end up with a 4-diode configuration. Notice here that we have ground, and here's our output, but our source is not tied directly to ground. And what we're going to try to do is make an output that looks something like this. The negative half is what we want to be efficient with. And the operation of this is maybe a little bit confusing. So if we consider the positive half of the wave, I guess you can say mode of operation, well, the positive terminal is going to interact with this diode D1, and it's going to go to some output, call it Vout, and that's going to go to some kind of load that's grounded, and that ground will be virtually tied, well, it will be physically tied to this ground, but on the schematic there might be some disconnect, and then that ground will have another diode. In this case it is D2. So that's kind of the mode of operation. Now if we look at the negative cycle half, so the polarity flips, now we're interacting with D4 to some output, goes to some load, which is probably grounded. That ground is connected here. And then we interact with D3 to complete that current loop back to the negative side of the source. So it's a flipping of using either D1 and D2 or D3 and D4. Let's consider this circuit right here. So we have our full wave rectifier, we tie in a resistor, and then we have a capacitor. We know that that will be for smoothing. So on the positive cycle, where we have the polarity as defined, we know that the current is going to take the blue path, so it's going to go from here to D1 to the load. So now we are at this resistor right here. From the load to ground, it's going to connect to this ground, and then this current is going to go through D2. So that's our current loop on the positive half. Now on the negative half, it flips and we go through D4 to the resistor to ground, and then that ground goes to D3 and then backwards. Now notice here, no matter which cycle we're looking at for the voltage source, we pass through two diodes. So we have a diode drop here, and then we have a diode drop here in the case of the positive cycle. So you would expect when you are probing your output, which is here to ground, well, you get two diode drops that you have to account for. And you also see that reflected in your smoothing capacitor calculations, which these are basic approximations. In the advanced electronics course, we'll go into the derivation. But for now, we're just introducing the concept. But you get a familiar term where you have the load current, or the expected load current, the period of this source right here. You get your specified voltage ripple that you kind of specify or you're given. And then you have this factor of 2, and that comes for the ride. Now if we build a circuit and simulate that, so we connected this line right here. So now we have a 1K resistor and a 10 microfarad capacitor. What you get here is the output is this green function, and your input voltage, so probed here to here, that's your red function. Now if you take the difference here between what you could call the amplitudes, what you're going to get is about 1.4 volts as a difference. So this right here peaks at about 3.4 volts. And then our amplitude up here is 5 volts. So we get that 2 diode drop coming through. Now one thing that you'll notice is that ripple, or that exponential decay, is a lot tighter because now we are using this negative half of the voltage cycle along with this positive half. So you get this doubling effect. Now this is useful not only because of the efficiency that we picked up from the negative half, but the capacitor that you now need is quite different than what you need for the half-wave rectifier, and that can be beneficial as well. So the last thing we're going to look at in this video is going to be the voltage clamper circuit. Now, this circuit here, it's quite odd. Would you ever see it in reality? No, probably not, but it's good for demonstration because it entails several diodes and a zener. Z1 with a 9-volt breakdown voltage. So we know if we are above that, we're going to clamp at that 9 volts. Then on this side, we have 3 of our general purpose diodes in series. Why anyone would ever do that, I don't know. But oddly enough, as this circuit is, we can look at the positive half of the input voltage. So what happens? Well, we know that D2, D3, and D4, those are going to be off because they'd be reverse biased, and we're going to assume that the leakage current is 0. And we know that D1 is going to be on once we get to some threshold, but we know that Z1 won't clamp until we get up to above 9 volts. And if we look at that voltage, what we can see is that we're going to clamp at 9.7 volts and then come down. And if we wanted to know the current, it would simply be Vs minus 9.7 volts divided by R1, and that needs to be greater than 0. Now if we look at the negative half, because D1 is going to be blocking, we don't even concern ourselves with this branch, although if D1 wasn't here, Z1 would just act like a normal diode and we would have a 0.6, 0.7 volt drop over it. But we know that D2, D3, and D4 will be conducting, and those voltages will be 0.7 volts for each diode, so 2.1 volts for all of these diodes combined. So what we can say is that if that input voltage is now minus 2.1 volts, and that output voltage would be stuck at minus 2.1 volts. And then we would just repeat this cycle for the positive and negative halves of the input voltage. So what we would get is kind of this asymmetric voltage clamping going on by using both diodes and zener diodes. Now what we can do is take everything that we've learned in previous courses and this video and kind of tie things together. So from the advanced circuit analysis course, we know what transformers are, we know how they act, and if we had something like a step-up transformer, so we took some voltage V, stepped it up to some extremely high voltage, call it VO1, and it's going to be an AC voltage. We're going to throw that through a full wave rectifier. And of course we have our smoothing capacitor to have a nice DC signal. And then we have some other circuit components, but we have a voltage clamp here. So while the circuit might not be, again, too useful, at least in the voltage clamping stage, the transformer and the full wave rectifier are very useful and very common. So this would be some big AC voltage, and then essentially what we would see is some quite smooth DC voltage. And this is kind of a very important concept when we talk about power electronics, but that's later down the road. For now, we can leave this here and move on to LEDs or light emitting diodes. If you learned anything new, learned anything useful, please like the video, comment, share, subscribe, all the fun stuff. We'll see you in the next video. Thank you for watching.